What's going on, guys? Welcome back to my channel. My name is Abbas and I'm a mechanical engineer. And if you're new here, I have a master's degree in mechanical engineering and I work in consulting as a mechanical designer right now. And I do have a very keen interest in aerospace design. And I'm starting a new series called Engineer Reacts, where I'll be reacting to any real world event that happens, any new tech that comes out, and just offer you guys an analysis and a breakdown from an engineering perspective. So the first episode of this series is the analysis and breakdown of the Boeing 737 crash that happened near Jeju in South Korea. And I don't want to go into the details of what happened. I don't want to second guess what the pilots could have done differently and all of that stuff. I'm not here to do that. I'm just here to give you an engineering perspective on the chain of events that led up to the crash. Okay, how mechanical factors, aerodynamic forces, system behaviors, all of that came together until the crash happened. And the goal is to basically help you understand the technical side of what happened, so you can see how these engineering elements played a role in the tragic outcome that occurred. So I'm just going to give you a brief overview of what happened. If you want more detail, you can check out any news channel to see what exactly happened in the event, in the unfortunate incident. But just a very brief overview of what happened was that, it wasn't a very straightforward hard landing. Basically, the reports indicate that there was a bird strike that occurred in one of the engines of the aircraft and during its approach on the runway. And that basically triggered a series of events that caused some critical failures. So ultimately, the plane ended up belly landing on the runway and it skidded along the runway until ultimately it couldn't stop, and until it collided with a barrier made of concrete, and ultimately it crashed and exploded, killing almost everyone on board, unfortunately, except I think 2 survivors who are, I believe, the cabin crew members who are sitting at the back of the at the rear end of the airplane. Okay, so as a mechanical engineer with a keen understanding and interest in aerospace design, I wanted to walk you through this sequence of events that happened, and we're going to examine each phase from an engineering perspective. Okay, and before I begin, I just want to say that the full investigation is still ongoing. I'm just some random guy on the internet providing a random analysis, making a random video. So I suggest that you take everything that I say with a grain of salt. Ultimately it's just speculation. You should wait for the official investigation to get done, to get some hard facts. Okay, so what I'm offering here is just an engineering perspective based on preliminary reports and known behaviors of aircrafts under similar circumstances. With that being said, let's get started in the video right away. So one of the biggest engineering headaches in aviation is something that sounds very mundane, but it's actually a very, very crucial component. It's actually bird strikes. Okay, now we're talking about birds literally flying into the airplane's engines, especially during takeoff or landing, where the jet is at lower altitudes. But it's a very, very major design consideration in aircraft design, and here's why. Because when you're building commercial jet engines, okay, like the ones in Boeing 737, the manufacturers have to prove that these engines can handle a certain level of bird ingestion. And it's exactly what it sounds like. They will fire bird carcasses, as you can see in the video. Generally, it's chicken or turkey types of birds into a running turbine on a test stand. And it's pretty grim, okay? But it's the only way to ensure that the engine won't just explode the moment a bird hits the fan blades. And the goal is to avoid what we call an uncontained engine failure. And what that is that, you don't want broken blades or any shrapnel busting through the engine casing and potentially damaging the plane's wing or the fuselage. An uncontained failure is very, very dangerous because engine fragments can cut fuel lines, it can cut hydraulic lines, it can sometimes even pierce passenger cabins. So that is why the engine core structure is designed to handle and contain most of the internal breakage. But now the reality of the matter is that the test standards can only go so far, because real birds, they come in all shapes and all sizes, and some weigh a few ounces, others weigh multiple pounds. Sometimes even flocks of smaller birds can get sucked in all at once, so it's it can exceed much far than what the engine was tested for. So the fan blades themselves are, they're made of titanium, they're made of nickel-based superalloys, which are very, very strong. But at takeoff and at landing speeds, the kinetic energy of even a single bird flying into the turbine, into the engine, can be massive, okay? And you have these blades spinning at thousands of RPM. Suddenly, introducing a bird is like throwing a chunk of like metal, into a high-speed fan. It can bend, it can fracture the blades, it can cause vibrations. It can also lead like to an ultimate shutdown if the engine computer senses, critical damage. Losing an engine at cruising altitude like 30,000 feet is very, very serious. But it is manageable. It is manageable because the flight crew has the time to go through the emergency checklist. Stabilizing the aircraft, diverting the aircraft to a nearby airport. But if this happens on a lower altitude, when the plane is like on its final approach, on its descent, then the margin for error is razor thin. And if the engine surges or flames out, then the pilots have a few seconds only to respond, like lowering their gear, adjusting flaps, deciding to go around. It's very, very hard. It's very, very difficult. And if debris from that damage severs like a hydraulic line or cuts, electrical cables in the aircraft, you're now dealing with like compound emergency where like multiple systems are compromised all at once. At that point, even the best design, the best backup systems can be put under a ton of stress. So, the entire idea behind like modern jet engineering is that if one engine fails, you should still be able to land safely. But then that also depends on the extent of the damage that occurred. For example, like if you end up with shattered blades, shattered engine, collateral damage to other critical systems, then it's like a whole new ballgame, So that is why like bird strikes are never just a small deal. Engineers plan for it, they test for it, but in the real world, it can still cause catastrophic change of reaction, especially when it happens during those critical phases where the flight is near the ground. So yeah, engines are tough and they're tested heavily for bird ingestion, but nature will still throw you scenarios that exceed the test envelope. At low altitudes, pilots have zero time to sort things out, which I believe what happened here. Things can go from bad to worse in a jiffy. So that is why bird strikes remain one of the trickiest engineering and operational challenges in aviation. So yeah, the next thing I want to talk about is redundancy. Redundancy basically means having backup systems so that if one fails, you're not suddenly in a hopeless situation. You still have time, you still have backup systems to save yourself and save the airplane from any hazards, ultimately landing safely. So most commercial jets have two engines. I'm sure you guys already know. One is powerful enough to keep the plane afloat and running if the other fails. So if the bird strike damages one engine, you don't necessarily lose the ability to stay airborne. You can still maneuver, you can still climb, you can even land on that single engine that is available. And that is, an intentional design choice because engineers specifically want to account for like a worst case scenario that could happen. Scenarios like an engine failure. Now, the engines themselves, the 737-800 uses high bypass turbofan engines. Now without getting too deep into the weeds, these work by drawing a huge amount of air with a big fan at the front, and some of that air gets directed into like a smaller core engine where it's mixed up with fuel and ignited, and that produces the power to spin the turbine, okay, which obviously generates the thrust. So the rest is bypassed around the outside, okay, which adds to the thrust and also makes the engine quieter and more efficient. And then there's the hydraulic side of things, and basically what this is that it's pressurized fluid lines that move critical parts of the airplane, like for example the ailerons, the rudder, the elevator, even the landing gear and the flaps. So the aileron will help you roll, the rudder will help you yaw, basically turn left and right, and the elevator will control the pitch of the aircraft. And the landing gear and the flaps are also controlled by the hydraulic system. So modern aircrafts typically have like multiple independent hydraulic systems. That means if one line gets punctured or loses pressure, then the other ones, are still intact and can be used. So let's say there was like a debris or mechanical malfunction, and one hydraulic line gets damaged, you still have another system that can keep those surfaces operational. It's like having like 2 or 3 separate, safety nets. If one tears, you've got another to catch you. So the engines of the aircraft typically have like hydraulic pumps attached to them, and as the engines spin, the pumps pressurize the fluid up to like thousands of psi. Think of it like a super strong water gun, but instead of water, it's like fluid designed specifically for extreme temperatures and pressures. Okay. And what the fluid does is that when the pilot moves a control column or flips a switch to, let's say, deploy the landing gear, for example, then the valves open up in the hydraulic lines, and then the high pressure fluid pushes the pistons and the actuators to physically move those parts. In other words, like the pilot's input tells the fluid, go here, apply force there, and that's how like the airplane's big, heavy surfaces actually move in real time. And what's key here is that the 737-800 and most modern jets, they'll have like 2 or 3 independent hydraulic circuits. So if something punctures one line, like debris or a bird strike or like metal fragments from a damaged engine, there's still another circuit still pressurized. It's pressurized, it's ready to handle the same tasks. You never want like single points of failure to take away your ability to steer or lower the gear. So the first layer of redundancy is a second engine being available. The second layer of redundancy is that, there is multiple hydraulic lines. The third one is electrical power, okay? So the main source of electricity in modern jets comes from the generators that are driven by the engines. But then there's also an auxiliary power unit. It's called the APU, okay? And it's usually at the tail of the aircraft. And this is like a third engine, but it doesn't really provide thrust. It can power the airplane's essential systems in the event that like a engine generator goes offline. So if you, for example, lose one engine, that the APU can step in, and it can provide electricity needed for navigation, for instrumentation, even for hydraulics. So it's like a small turbine. As I mentioned, it's located in the tail of the aircraft. It doesn't provide thrust to push airplane forward, but it generates electricity. Okay, it generates electricity. Sometimes it can even generate pneumatic air power. So in a normal flight, each main engine has like a generator, that powers the aircraft's electrical systems. But let's say, for example, you lose one engine or even both engines are out, you still have the APU to keep those critical systems alive. So imagine your cockpit screens, the navigation computers, radios, hydraulic pumps, all of that needs power. And the way it works is that the APU is basically like a smaller, version of a jet engine that drives the generator. So pilots can switch it on manually, and it can be even switched on automatically if needed, okay? So it runs on the plane's fuel supply, it draws outside air, it spins, and it generates a steady stream of electricity. So to put it simply, there's multiple layers of safety approaches that are designed, okay, to keep an airplane to be able to maintain basic functionality and safety in the event that something goes wrong. For example, in this instance, a bird strike, okay? Losing one engine in theory shouldn't doom the aircraft for failure, okay? You can still deploy the landing gear, you can still manage your flaps to slow down properly for landing, you can still power critical flight controls. And of course, all of that hinges on the fact that the flight crew, knows the proper procedures, they can stay calm, they can execute the right actions in the cockpits. But from an engineering standpoint, the plane has the capability built in. So when you hear about an engine failure or major system faults, remember that airplanes are designed with multiple backup systems. This is why commercial aviation is safe. It's safer than cars. If you look at the statistics, there's more crashes that happens in cars and more accidents in cars and vehicles than airplanes. So even if one piece of the puzzle breaks in an aircraft, there are other pieces ready to take over and keep the aircraft flying safely. Now, if you circle back to what happened in this crash, the Jeju Air Flight 2216, you might wonder, okay, if you lost one engine due to a bird strike, why didn't the backup systems keep the plane under control? And that is the big question. Okay, that is a big $1 million question. Normally, the plane should still be controllable. The pilots should be able to deploy the landing gear with hydraulic pressure from the systems. You can even rely on the APU for extra power if needed, to land safely on one engine. But the fact that the aircraft ended up belly landing raises a serious question. you know. Why did it crash on the concrete wall? Why wasn't it able to deploy the landing gear on time? Was there additional damage that occurred, you know, because of that one engine? Maybe, you know, there was a chain of reaction that occurred from that one initial bird strike. Smaller failures cascaded, you know, eventually in the entire aircraft. Maybe some hydraulic lines were burst. Maybe we don't know, honestly speaking. You know, it could have been a chain reaction of smaller failures that overwhelmed the crew as well. Maybe because of stress and confusion, the pilots couldn't, you know, couldn't deploy the landing gear. Or maybe multiple backup lines were compromised from that initial bird strike. From an engineering standpoint, losing one engine alone rarely leads to a catastrophic outcome, theoretically speaking. You know, because the planes are literally built to handle that exact scenario. But as we can see with this crash, if multiple layers get compromised, or if the crew can't execute the steps needed to switch those backups, which I'm not saying that's what happened, but it is a possibility, okay? Then the outcome can still be tragic. And that is why every single system in an aircraft is tested again and again. And pilots also practice and for these emergency procedures rigorously. Because at the end of the day, it's about stacking the odds of survival and control in your favor, you know, even if unexpected events happen. So now let's dive a little deeper into the landing gear and the flaps, because, you know, as we know from the crash, the landing gear wasn't deployed, the flaps were very minimally controlled, and let's see what happened. So let's analyze how it's supposed to work in a normal landing compared to what happened in the Jeju Air incident. Okay, so coming to flaps. Flaps are basically those moving surfaces on the trailing edges of the wings, as you can see here. Okay, so in simple terms, they change the wing's shape and size, so that you get more lift, basically, at slower speeds. Because normally when you're coming in to land, you want to slow down without losing too much lift. Otherwise, you drop like a rock. You see, so flaps help with that. So they usually extended progressively. You know, first with like a small flap setting, and then a little bit more, and then finally like a full landing configuration, given that the runway is long enough. So that keeps the plane nice and stable, and it gives the pilots, you know, better control at slower speeds. Now in a situation like the Jeju air crash, if the flaps weren't fully deployed, or if they couldn't be deployed for whatever reason, then the airplane would be coming in faster and would be harder to handle on the runway, which is what we see happen here. You see, we're talking about like a bigger risk of overrunning the runway or losing control if something else goes wrong. And then there's the landing gear. Now an airplane's landing gear is retracted. As you can see in this video, it's retracted during the flights to reduce the drag, okay? Because otherwise you'd be burning a ton of extra fuel dragging those wheels throughout the air, okay? The aerodynamics just wouldn't be as efficient. So typically the landing gear is deployed, you know, using hydraulic actuators. Sometimes there's electric motors, and many aircrafts also have a backup system, like a gravity drop or like a manual drop, you know, manual crank, just in case, you know, you lose hydraulic pressure in the main hydraulic lines. So when the gear extends, it locks into place so you can support the airplane's weight on the touchdown. Because if you think about the forces that are involved, literally tens of thousands of pounds slamming on the runway, you know, so obviously it has to be built tough. But you know, when building an aircraft, this part is very, very systematically and efficiently designed to be able to absorb and distribute the entire impact energy across the aircraft's structure. Okay, so in a normal landing, you've got both flaps extended, okay, so that you're stable and you're slow enough. And then the landing gear is also down so that you can, you know, roll safely on the runway. But in a belly landing, which is what happened here with the Jeju Air, is that you're missing both of those safeguards. You're essentially scraping the fuselage on the runway, which is the belly of the plane, right, across the surface of the runway. And that part of the plane is just not meant to handle that kind of friction and stress. And that is the reason that we have wheels, okay, because imagine the friction and the heat generated from metal grinding against concrete. It's enough to spark fires if the fuel tanks or the fuel lines are compromised, you know. And because engines on the 737 hang beneath the wing, as you can see, they can strike the ground first in a belly landing, okay? And that can even tear them off easily, which potentially like rips open parts of the fuselage and the cabin, even the wings. Now in the Jeju Air 2216 crash, aircraft did end up belly landing. So it was a belly landing situation, no gear, minimal or no flaps, and that is likely part of the reason that it skidded off the runway and it slammed into a concrete wall, as you can see. So the plane just couldn't slow down, and the friction points were very minimal as well. It was like the bottom tips of the two engines and the tail and a little part of the tail of the aircraft. So there was just not enough friction to slow down the airplane. So instead of using wheel brakes or thrust reversers on the engines, assuming the engines were still functional, everything came down on the underside of the fuselage. And combine that with like the initial bird strike, which might have compromised, the hydraulic systems or the confusion in the cockpits, you've got a recipe for disaster, which is what happened here. And so from an engineering perspective, it's not that the 737-800 design is flawed. It's not that. It's just that, these systems exist for good reason. But if they're not successfully deployed, whether due to mechanical damage, pilot's error, cascade of failures that happen from the initial bird strike, then you lose the crucial layers of safety. Okay, and that's exactly why belly landings can be so catastrophic, as you can see. So yeah, the flaps and the landing gear might sound very basic, but they're actually very, very critical systems and components in an aircraft. Okay, and that they allow for the aircraft to have a very soft, controlled touchdown. And when they're absent, for example, in a belly landing, it really underscores how much of a difference they can make in dissipating that energy of landing and keeping everyone safe, Because when a plane lands on its fuselage instead of its wheels, it's like all of that metal scraping along the runway, which then creates two major problems. First one is friction, okay? And you can think of it like dragging a metal plate along like a sidewalk, except like you're going at like 100 plus miles an hour, and the belly can heat up to enormous amounts of temperatures very, very instantly. So now let's talk about the loss of braking control, because wheels on an aircraft have very, very powerful brakes. It's like a car's, disc brakes, but scaled to a very big level. On top of that, you can also use thrust reversers on the engines to slow down the aircraft. But when the plane is sliding on its belly, all of that is gone. Okay, because it's like trying to stop a sled on an icy hill. There is just no way to control your deceleration. You either overshoot on the runway or you skid off to the side. And this ties back to the Jeju air crash because the landing gear just wasn't down. The pilots had almost no way to modulate the speed or direction once the plane was on the ground and started sliding, So that is why he went, off the paved surface and struck a wall beyond the runway. And had the wheels been down, there would have been a fighting chance to brake or steer the aircraft. So yeah, lastly, in terms of belly landing, there can also be structural shear, that can occur, which is basically a belly landing tearing open the fuselage. Because planes are designed with very strong underbelly structures, but not necessarily to withstand the impact from like a massive load like this at landing speed. And even if the fuselage doesn't rip, you still have like engines slung under the wings. So those can break off if they hit the ground first. So yeah, all of that wreckage can, cut into the wing. It can rupture fuel tanks. It can sever very, very crucial control lines as well. And if you're unlucky enough to hit a concrete barrier, just like it tragically happened with the Jeju air flight, the deceleration forces are so enormous in a split second that level of force can just crush the cabin. And that is why we see a very high rate of fatalities that occur whenever there is runway overruns that end up with collisions. Now, when we talk about the runway overruns, we can't just focus on the airplane itself. We have to look at the infrastructure, the runway infrastructure around it. Because sometimes it's the design of the runway and what's beyond it that is going to decide the difference between a catastrophic crash and a survivable skid. So a belly landing plane is very vulnerable because there's just no gear to absorb impact energy, If you have a wall located just like a few hundred feet past the runway's end, you're basically, you basically eliminated any chance for like a sliding aircraft to come to a stop effectively. And in this crash incident, that's exactly what happened. You see, after the plane touched down without its gear, it slid right off. Right off the runway, struck a hard obstacle because it was belly landing. The flaps were minimal, there was no landing gear, there was no braking system, and it just resulted in a very, very violent deceleration and a massive fire. Had there been open space, or had there been a crushable zone beyond the runway, maybe, just maybe, it wouldn't have been as catastrophic as it was. So how does this relate back to Flight 2216 Jeju Air? Well, the airplane was already in trouble. Damaged engine, belly landing. Okay. But if you look at other runway incidents, sometimes aircrafts end up damaged but still keep casualties to the minimum, because it either stops on a safety area or just slides onto safe ground. But in this case, the final straw was a solid wall. And you can imagine the destructive power of a 60-ton aircraft colliding with an immovable barrier at super high speed. And that is why airport design isn't just about having a smooth runway, it's actually about planning for the worst. If a plane can't stop in time, what is waiting for it beyond the pavement? Do we have a compressible arrest bed or an open field? Is there hardened structure blocking the way? And sadly, the Jeju Air incident just shows how crucial these questions can be. Now, one thing that engineers can't really control is the human element. Because we can design a plane like the 737 with multiple backup systems. These redundant hydraulics, robust engines, sophisticated computers. But if the pilots cannot respond correctly under pressure, then all of that engineering can only go so far. Now, pilots have checklists for just about every emergency scenario that you can imagine, whether it's engine out procedures, bird strikes, hydraulic failures. And so the idea is to break down a crisis into a series of steps so that you're not only relying on the memory alone. Now, under normal conditions, these checklists are lifesavers because they keep everybody on the same page. But in an incident like this Jeju Air Boeing 737 incident, if there was a lot of confusion and just a lot of time pressure, then the crew could have been overwhelmed. And missing key steps like extending the landing gear or not knowing which engine is failing and shutting off the wrong engine, that could lead to catastrophic events, even if every other mechanical system in the airplane is working properly. And look, let's face it, in an emergency like this, the stress levels are through the roof. Pilots train to handle these levels of stresses and crises in simulations, but in real life, real life can throw just unexpected variables at you. Maybe the bird strike was more violent than what you trained for in a simulation. Maybe they misread what engine had failed. It's happened before, guys. It's really happened before in aviation. Pilots have accidentally shut down the good engine instead of the bad one. So, yeah, connecting that to the Jeju air crash, it is entirely possible that the flight crew was dealing with partial engine failure, alarms, time pressure, all of these things, all of these factors at once. And if they missed a step or two or got turned around with the chaos, then the aircraft design just cannot magically fix that. So redundancy and backup systems rely on human input. That's engineering safety 101, Human input is necessary to activate the right systems at the right moment. So yeah, even though the 737 is built to fly on one engine, there's a limit to how much complexity you can pile on the pilots in an emergency like this before mistakes happen, So there might be a backup for the hydraulics, a backup for the electrics, but each backup requires a very specific procedure to activate it. So if you're flustered and you don't have really too much time to go through the entire checklist, you can end up with half of your systems still going offline because simply you haven't flipped the right switches. It's that simple. So that is why aviation accidents, they often reveal a chain of seemingly small errors, any one of which might have been harmless on its own, but together together, they become overwhelming. So for the Jeju Air 2216, having a bird strike disabling the engine should have still been survivable on paper. But if the confusion led to not being able to deploy the landing gear, or shutting down the wrong engine, or not being able to control the flaps properly, then suddenly the airplane's brilliant engineering gets bypassed. So yeah, I mean, this is what I find so distressing about this Jeju Air tragedy, is because, you know, the 737 is a pretty resilient aircraft. It's one of the most popular aircrafts in the world right now, you know, and it's designed for an engine-out flight. It has hydraulic and electric backups. Yet the crash still happened. You know, so this tells you there is a possibility that there was a human factor involved. I'm not saying there was. This is just speculation. Again, I'm just a random guy on the internet, but there was, from my understanding, I think there was likely a human factor that played a role in this. You know, whether it was stress, whether it was confusion, I don't know. Maybe it was just the heat of the moment. You know, it did end up causing crucial steps to be missed. So yeah, I mean, no matter how many fail-safes you build, a series of human missteps can literally, you know, defeat them. So yeah, I mean, the real lesson here is that, you know, engineering alone cannot guarantee safety. It cannot. It has to be paired with calm, methodical execution by the people flying the plane. So if you break that link, if the checklists aren't followed properly, if there's panic that sets in, then all of the backup systems in the world will not be able to save you. You know, and that is exactly why the human factor remains one of the biggest variables in aviation accidents. So we'll have to wait for the official investigation reports to get the full story. But I hope that today's overview can help you see how some mechanical and aerodynamic factors stack up to create this type of emergency. With that being said, I hope you guys enjoyed this video. If you did, make sure you hit the like button and subscribe to the channel if you haven't, because I'll be posting a lot of engineering content that you don't want to miss out. Thanks for watching, and I'll see you guys next time. Peace!